Mm. Hi Sushant, how are you? Hello, good evening. Charan. Hi Sushant. How is everyone? Chaliye, let's start now. Okay, right? Should we continue now? Please tell me, is it audible?
Yes, sir.
Right. Okay, let's start now. Okay, so last class we discussed was up to this, isn't it? The potential difference we have calculated, okay, due to uniformly charged sphere, है ना? Non-conducting sphere also we have discussed, okay na, conducting sphere as well as the non-conducting sphere we have discussed. Okay, now let's discuss an example here. In this question, what is given to us? Let's say, okay, in this example it is given to us a charged sphere is given to us. Okay, a uniformly charged sphere is given to us, and in front of a uniformly charged sphere, it may be a conducting sphere or non-conducting, because we are not worried about what is happening inside. Okay, so that's why here it is not mentioned what kind of a sphere is, but one thing it is mentioned that the radius of a sphere is r and the total charge given to this is the q. Okay, now along this line there is a charge particle here. The particle charge is minus q and the mass is what? M. Okay, and right now this particle is what? At a distance 4r from the center of the sphere. Okay, so we have to find out in this question, find, okay, in this question let's find out, find velocity of charge particle, find velocity of charge particle, charge particle when it reaches, when it reaches the surface of a sphere. Okay, when it reaches the surface of a sphere, then we have to find out what will be the velocity of this charge particle. So please tell me what we will have. Please tell me what we should apply it again in this question. Please tell me. This is a fixed sphere. Okay, this is what kind of a sphere? This sphere is fixed right now. This sphere is not going to move anywhere. So we have to find out in this question what will be the velocity of charge particle when it reaches the surface of the sphere. So tell me what we should use it. Can we apply the energy conservation in the question? Please tell me. Can we apply the energy conservation in this question? Because again, the only force here is acting is the electrostatic force, isn't it?
Yes,
Electrostatic force between the two charge particle, not particle. One is the sphere, another one is the particle. So please tell me what will happen here. Let's apply the energy conservation and tell me what is the answer we are going to get it after the application of energy conservation. Will you try the equation? Please tell me. Today we have to mostly discuss about the problems related with the concept we have discussed yesterday. So please tell me. You also try it once, okay? Please try this question once. Apply. This is going to be what? This is going to be your initial point. Initially, the particle is released. Okay. Initial particle is what? It is released. The initial velocity is zero, and finally the particle is going to reach the surface. Okay, so please tell me how much will be the velocity of this charged particle when it reaches the surface of the sphere.
1 minute. So try.
All of you, will you please try this one? Everyone joined, or
So
anyone
try.
is still? Yeah, Shashank, Charan, and Lokesh. Yeah, all of you joined. Manal is still absent. Okay, chaliye. Please try all of you this question. Okay, tell me what is the answer coming to us when it reaches the surface of the sphere. Okay, surface of this charged sphere. What will be the uh, velocity of the charged particle? This is what we have to find it out in this question. Okay, just try for a minute and tell me what is the answer we are going to get it.
So is it root over 3 q by 2 rm?
Let's check it. See, what will happen? We will apply the energy conservation. The initial velocity 0, the initial kinetic energy 0. Initial potential energy will be what? So initial point, let's first find out what is the potential. The point is outside. The potential will be how much? Kq by 4r multiplied by charge. That is the potential energy initially. And potential multiplied by charge gives us the potential energy. Next, when it reaches the surface, the kinetic energy is how much? Half mv square. And what is the potential energy now? So when it reaches the surface, what is the potential on the surface of a charged sphere? So potential on the surface of a charged sphere is kq by r. Again, I will multiply by charge. That makes it potential energy. Okay. So if you simplify it, what we are getting? K capital Q small q by 4r. Send it other side. The K capital Q small q by r, and that should be equal to half m v square. Okay, if you simplify it, K capital Q minus 1 by 4, that will be 3 by 4. And next we have half m v square. So if you simplify it, this 2 and this 2 will get cancelled out. So what is the velocity we are getting? 3k capital Q small q by 2 rm under root. So this must be the velocity of charged particle when it reaches the surface of this charged sphere. Is that clear? So this is what they asked in this question. Is that clear? Please tell me.
Yes, sir.
Now, the same question I'm going to make a little bit difference here. What is the different I'm going to give you in this question? In this question, instead of giving you a conducting charged sphere, what I'm going to give? I'm going to give a uniform charged sphere. Okay, what kind of charged sphere? It's a uniform charged sphere, means it is a non-conducting sphere. Okay, it is a uniformly distributed charge is there throughout the volume of the sphere. This is the center, and this time what I'm going to do it, I'm going to just make a tunnel here, a very thin tunnel. Okay, so that the charge does not changes. When you will make the tunnel, you will be thinking, Oh, sir, some of the charge of this sphere is gone. No, no. This is a very thin tunnel. So that whatever is the charge on this sphere, it is still Q only, and the shape remains what? Still spherical. Understood? This is a very thin tunnel we have made it something like this. Okay. Just for showing purpose, I am making it bigger in the diagram, but it's a very thin tunnel has been made. Understood? Thickness of the tunnel is what? Very small. And a particle is thrown again from what? From this point. Okay. Understood? Again, initial velocity I am taking 0. Particle mass is m and the charge is what? Minus q. Now it is thrown, right? Or released, you can say that. Now they are asking in the question, when it is reaches, it will go na, it will go through the tunnel, isn't it? It will go through the tunnel. So now they are asking from the center, when the particle is r by 2 from the tunnel center, sorry, or a sphere center, what is its velocity? Same question is there. Only thing is what? In this question, I changed the distribution of charge. Instead of giving us the surface charge density, I gave the volumetric charge density. That is the one change I have done it in the question, right? And the second thing, what? It's not a conducting one. It is what? It is a non-conducting one. Okay. So find the same thing again in this question also. Find the velocity of particle. Okay. Velocity of charged particle. So here also the concept is going to remain same, energy conservation. But here you have to apply the energy conservation little bit carefully. Okay. Find the velocity of charged particle when.
Sir, won't we apply a work energy per like the work energy theorem? Because the potential inside the non-conducting sphere is always different, right? So at different places we get different. So until up to r by 2 radius, so different type of potential is there.
Yes, that's what we have to apply it. And it's a non-conducting sphere, so different point will have different potential energy. So it will keep on changing, as we go in this tunnel. Okay. If it has been conducting, everywhere the same answer will come. All the inside point will have the same velocity. But here it will change. So here we have to apply between the initial point and the point where they are asking me to find the velocity. Okay. When it is r by 2 distance from the center. And do we know what is the potential inside a non-conducting sphere? K cube by 2r cube 3r square minus small r square. That's what we have got it in the yesterday class, isn't it? R by 2 distance from the center. Okay. So again the concept is same, application of energy conservation, but little bit different formula we have to use because the situation is changed in this question. So please apply the energy conservation between your initial point and final point. Initial point is what? Your point of projection. The initial point you have zero kinetic energy but some potential energy. And when it reaches this point, right? When the particle reaches this point, it will have some velocity. So it will have some kinetic energy and as well as it will have some potential energy. So please write all the expression carefully and tell me what is the answer we are going to get it in this question. Please tell me, understood the question? Both questions are similar. Only what is different? The distribution of charges different in the two example we have taken. Okay. In this case, this sphere is a non-conducting sphere. Okay. Non-conducting solid sphere. Please tell me what we are going to get it now. Take 1 or 2 minute time and tell me. Write the equation at least. We have to apply the energy conservation carefully in this equation also, and we will get our answer.
Sir, initially the particle is at what distance, sir?
Okay, that distance I forget to mention. Let's take it 4r again. Initially, the particle is 4r from the center. Yeah, initial distance is needed now, because then only you will be able to write the potential energy initial one. So let's take initially the particle is what? 4r from the center. Can we write the equation now? Please tell
Yes,
me.
sir.
Initial kinetic energy 0, right? Initial potential energy will be kq by 4r potential written multiplied by charge becomes potential energy equal to. Finally, when it reaches the point where I want to calculate the velocity, let's say its velocity is something v. So kinetic energy will become half mv square plus. When it reaches that point, will it have some potential energy? So let's write the potential energy there. So at that point, we have to write first the potential, and then I will multiply the charge present at that point. That makes it the potential energy. So what is the potential at that point? Kq by 2r cube into 3r square minus x. X means what? Distance from center to that point. Okay, this is the potential at that point. Let's multiply the charge present there. That makes it again what? That makes it again as the potential energy. Now simplify it. K capital Q small q by 4r we have minus here equal to half mv square plus, or better to say minus here, right? K capital Q small q by 2r cube and 3r square minus r square by 4 we will have, right? K capital Q small q by 2r cube and 3r square minus r square by 4. So 4 into 3, 12 minus 1, 11 r square by 4 will come. So if we simplify this equation, we are getting half mv square equal to minus k capital Q small q by 4r plus k capital Q small q. And if you look at here, r square and rq will get cancelled out. So k capital Q small q 11 divided by 4 into 2, 8r. Now we will simplify it, okay? Just one, two more step and we will get our answer. K capital Q small q by 4r is taken common, right? 4r is taken common. So we have 11 by 2 minus 1, okay? Now just last step, what we have? Half mv square k capital Q small q by 4r and 11 minus 2. So 9 by 2 we have, right? Half and this 2 got cancelled out. So what is the velocity we have? Velocity we have 9k capital Q small q by 4 rm. This is the velocity of the charged particle at this point. Do you see that both the question are what? Both the question are the application of what? Application of how do we write the potential due to a conducting sphere and potential due to non-conducting sphere. First example was the writing the potential due to a conducting sphere if the point is outside the sphere and if the point is on the surface. This question is what? writing the potential due to what? A non-conducting sphere. In the two cases, right? Initially, the particle is outside the sphere, so we wrote the potential at outside, right? And then when the charged particle came inside the sphere, then we again wrote the potential inside. Is that clear? Please tell me, clear up to this? Now, one very nice example is there. Will you try that example? You are going to learn a question here. Please tell me, if I give you a question like this, let's say this is a sphere, okay? And this is a charged sphere. Let's say this is a charged sphere given to us. The charge is something q and radius of this sphere is r. Okay, charged conducting sphere. Okay, let's take it. What kind of a sphere? A charged conducting sphere is there. So please tell me here. It's a positively charged sphere. Okay, let's say along this diameter line I'm going to keep another charged particle, but the problem is what? This other particle is also positively charged and it has some mass in it. Please tell me, can this positive charged particle reach the conducting sphere? Please tell me. By its own, by its own, on its own, can it reach the surface of the conducting sphere? No, na? Because it will be repelled by the conducting sphere, isn't it? Both are positively charged, so it's not possible for the charged particle to reach the surface of the conducting sphere, isn't it? So if I give some minimum velocity, then is it possible for the conducting sphere, sorry, this charged particle to reach the conducting sphere? Please tell me. Please tell, do you understand this question? The question says that if I want this charged particle to let it reach this point, then what I have to do? Do I have to provide some minimum velocity so that it will be able to reach it? Please tell me, is that part clear or not? So, what is that minimum velocity needed? Actually, that is what they are asking. Understood? So, if you see this question, you will say, sir, again, I will apply the energy conservation, right or not? And I will get my answer. Very good, correct. Right? This question is exactly that, okay? But why I am discussing this question? Because the next question I'm going to discuss with you, in that one, you have to decide within what point you have to apply the energy conservation. Please tell me, understand the question? Please tell, understood the question? So here in this question, what happened? Here in this question, what is the minimum particle velocity is required so that it will be able to reach the surface of the sphere? Because it's a positive charge. Without providing the initial velocity, it is not going to reach the surface of the other one. Okay. So what I will do it, I will think that okay, initially the particle is here. Let me give the minimum velocity so that it is just able to reach that. Just able to reach means what? Means, can I say the final velocity becomes approximately zero? Then what does it mean? It means the particle is just able to reach that final point. So that's why question asks what? Find minimum velocity needed. Okay. Minimum velocity needed by charge particle. Okay. Needed by charge particle so that it reaches the the surface of surface of the charged sphere. Understood the question? Surface of what? The charged sphere. So again, I am going to apply the energy conservation in this question. Okay, what I will write? Initially, I need to give some velocity. So that is what I have to calculate. So half m v minimum square initial potential energy kq by 4r into the charge, because now it's a positive charge particle, isn't it? So potential is kq by 4r multiplied by charge. That makes it the potential energy. Finally, kinetic energy 0, because it is just able to reach that, plus final potential energy k capital Q by r into the charge. So that gives us the minimum velocity requirement. Understood? How much we are getting? K capital Q small q are common. 1 minus 1 by 4. That is 3 by 4. So check it. Am I getting the same answer as the first question yesterday? Are we getting the same answer as the first question when we were discussing? Please tell me. So same way the question can be asked, understood? But same question is there, same calculation, same answer, but the statement of the question is what? Different. Please tell me. Clear this one?
Yes, sir.
Um, Now let's do one last example on the energy conservation, and this is going to be a really interesting one. Why? See, in this question, what I'm asking you, let's say I'm giving you two sphere. One sphere has what? Q charge and radius r, and the other sphere has what? It has 2q charge, and let's take the radius as something 2r, and the distance between these two center, that is 2r, this is r, 3r, so let's take it something 6r. Okay, just give me a moment. kq by, little bit easier. If I take it 2q na, then calculation will become little bit difficult. Okay, this is what given to us in the question. Is that clear? Please tell me, first of all, do you understand the question? This is the line joining their center. The problem is what? The problem is there is a charge particle here. It's a what kind of charge particle? Let's say it is a negative charge particle. Okay, it is what? It is a negative charge particle given to us in the question. This negative charge particle is on the surface of the second sphere. Okay, so please tell me, this negative charge particle having charge something minus q and mass m, will it start moving towards the sphere 1? Let me write it. This is the sphere 1 or sphere A, and this is the sphere B. Tell me. Please tell me, if I keep the charge particle on the surface of sphere B, will it move towards sphere A? Can it move towards sphere A? Please tell me.
Not
By its
directly.
own? No. Why not? Because it is going to be attracted by both the sphere, na? Both are positive charged sphere, isn't it? This is plus q. This is plus 4q, isn't it? So both sphere will be attracting, but who will be attracting more? 4q will be attracting more. So on its own, this charge particle is not going to reach the surface of the other. So that means what? Does that mean I need to give some initial velocity, so that if I give some minimum velocity, then it is possible for the charge particle to reach the other sphere. Understood or not? Please tell me. So my question is, what is that minimum velocity required? Okay, my question is what? Find minimum velocity needed. Okay, find minimum velocity needed so that particle is able to particle is able to reach the surface of other sphere or surface of sphere A. Understood the question? What is the minimum velocity I should give so that it will be able to reach the sphere A from what? Sphere B. It is just like a situation between the two planets, isn't it? If you want to send one object from one planet to another planet, let's say it is a straight line motion, then you need to give it some minimum velocity so that it will be able to reach the other planet. So what is that minimum velocity needed? Can you tell me what are you going to do it in this question also? This is your initial point.
energy conservation
Okay,
concept.
what is going to be your final point? Is this point is going to be your final point? Between these two points, you are
No,
going
sir.
to apply the energy conservation?
No, sir.
No. Why not?
Because at some distance
Correct.
between
We
them,
don't.
so until then, if we find the speed, then automatically it will pull the negative charge towards itself.
Yes, that's correct. That is the concept behind this question. We don't need to apply the energy conservation here between what? Between that initial and final point. We need to only apply the energy conservation between initial point and null point. Null point is what? It is the point where the net field is zero. So, right of the null point, field due to a sphere B is more, and left of the null point, see that I have marked a point called null point. Can you see that? I have marked a point called null point. Okay, so right of the null point, sphere B is creating more field, and left of the null point, sphere A is creating more field. So if somehow I manage to send the particle to the null point, what will happen? After that point, it will be automatically attracted towards the sphere A. So we need to only provide enough velocity to reach the null point. Okay. So that's why to solve this question, two important things is needed. One is the energy conservation between initial point and null point, and second is how to identify where is the null point. Understood? And null point means what? The point where the net field is zero. So let's say the null point exists at this point, and I'm going to just assume the null point is x distance from the center of sphere B. So that will become 6r minus x from the center of sphere A. All the distance I am measuring from the center. So please tell me, to find null point, what I should do first? Field due to a sphere A. Field due to a sphere A will be kq by 6r minus x whole square, and field due to B will be k 4q divided by x square. That's why I take the charge like that, so that taking a square root will be a simple thing, है ना? So k and q got cancel out. We have x square divided by 6r minus x whole square equal to 4. Take the square root, x divided by 6r minus x equal to 2. So we have x equal to 12r minus 2x, है ना? तो 2 plus 1 3x equal to 12r. That means x is coming how much? 4r. So now we locate the null point. Now we know that this x is what? 4r for us. Now let's apply the energy conservation between these 2 points. चलिए, tell me, write the initial kinetic energy half mv minimum square. That's what I write it. Plus initial potential energy. Initial potential energy due to a sphere A, tell me how much it will come. So for a sphere A, if I am writing, will it be equal to k q by 4r? Please check it. Because 6r is the distance between the sphere. Na? Initially the particle is here. So from center of sphere A to this point, the distance is 6r minus 2r, which is the 4r, into the charge minus q, plus due to a sphere B, kq by 2. Wait. Due to a sphere B, k, charge is 4q, surface point is there, the 2r is the radius, into minus q. That is my initial kinetic energy plus initial potential energy. Finally, when it reaches the null point, I just gave enough velocity to reach there. I don't give any extra velocity, okay? That's why I'm calculating the minimum velocity. Potential energy, so K due to a sphere A, K Q by, what is the X we have calculated? 4R. So 6R minus 4R, that will become 2R into the charge, plus K 4Q due to a sphere B, the distance from center become 4R into charge. Understood? Initial kinetic energy plus initial potential energy equal to final kinetic energy plus final potential energy. And between the sphere, you don't need to write it. Why? Because both the sphere are the fixed sphere. So whatever the initial value will come for these two sphere, same value will come for these two sphere finally also. That will cancel out in the calculation. That's why for the sphere pair, you don't have to write it. Okay. Now just a small simplification is needed now. Half m v minimum squared. Send it other side everything. K capital Q small q by r common, right? K capital Q small q by r common. It is minus 1 by 4. Wait, I have sent it other side now. Other side of the equation, so it will become plus 1 by 4. Then it will be plus 4 by 2 minus 1 by 2 minus 4 by 4 gone. This is what we have. Okay, just be careful about the calculation. That's it. Now let's simplify. Half m v minimum square, right? 1 by 4 plus 2 minus 1 by 2 minus 1. Okay, just that addition subtraction is needed, isn't it? Once we finish that one, we will get our answer. K capital Q small q by r, that is 1 by 4 plus 4 by 2 means 2. 2 minus 1 is 1 minus 1 by 2. Okay, so half mv minimum squared into 1 by 4 plus 1. So 1.25 it will become minus 0.5, 0.75. That means 3 by 4, right? So we got our final velocity requirement as how much? Half and 2 got cancelled out. What is the minimum velocity needed now? Under root of 3kq, 3k capital Q small q by rm2. Understood the what we learn in this question? Two things we learn in this question. First one is why I only need to send it to the null point, because after that it will be attracted towards the sphere and it will definitely reach the sphere A surface. So we don't need to give it enough velocity to actually reach the sphere A. We just need to give the velocity just enough so that the particle will be able to cross the null point. If it crosses the null point, it is definitely going to reach the other sphere or the sphere A. How to find the null point? So null point is a point where the net field due to the arrangements of charge is going to be 0. So that's why what we did, we made the field due to A and B sphere equal and opposite. That gives us the null point, and then we apply the energy conservation.
Sir, like Or can we tell as where the force is zero, there is the null point?
Yeah, that's it. Same thing. Na? Force is zero or field is zero. Same thing,
Yes, yes.
right? Null point means what? The point where the field is zero. If a point is there where field is zero, the force is equal to what? Charge into field,
Charge into
isn't it?
field.
So if I got the field equal to zero at that point, that means force also will become zero, na?
Yes,
So null point is the point where whatever charge you keep there, plus q, minus q, 5q, 15q, any charge you keep it at the null point, that's going to experience zero force there. Okay, so null point is the point where, irrespective of the charge particle nature and the magnitude, that is always going to experience how much? The zero force on it. Understood? Now, sometime what will happen in the question, they will give you a question like two spheres are there. They have been given some charge, and now they will give you, they are brought in contact with each other. What will happen if I bring the two charged sphere in contact with each other? What is going to happen? Can you tell me what is going to happen if I bring the two charged sphere, two charged conducting sphere, if I bring in contact with each other, what is going to happen? Are the charge transfer is going to take place?
yes, sir.
Right. Charge transfer will take place. So how much will be charge on each of the sphere after the transfer will complete?
Both will be equal charges. I mean, the potential will be same between them.
Yes. What will be same for both the sphere after they brought in contact with each other? They will have equal potential. Can they have equal charge? Yes. But will they always have equal charge? No. Understood? But what is going to be same always whenever they are brought in contact with each other? They are always going to have what? Reach equipotential. Right? Whenever two conductors are brought in contact with each other, or they are just connected by a conducting wire, both are same thing, है ना? Connecting them with a conducting wire or bringing them in contact with each other, it's the same purpose. What is the purpose of this thing? To make the potential what? Equal. So when the charge will also become equal, if both the sphere has equal radius, then what will happen? Then what will happen? Then they will have the equal charge also. But if they are not having equal radius, then charge won't be equal. Only thing what will be equal is their potential. Okay. The connection of two charged conducting sphere. Let's see what is going to happen. Okay, let's bring two conducting sphere, two charged conducting sphere in contact with each other, and let's see what is going to happen. Again, we are going to use the concept of the potential only. Okay, let's say this is the sphere 1. Okay, I am taking the radius of sphere 1 as r1, and there is another sphere. Okay, radius of this sphere is what? r2. Initially they had some charge. Okay, initially they had some charge. Now I brought them in contact. This is what? It's a conducting wire. Same thing, they are brought in contact or they are connected by a conducting wire. Exact same purpose. Can you tell me what will happen now? After bringing them in contact, can I say this is going to have some Q1 charge and this is going to have some Q2 charge? Please tell me. After bringing them in contact with each other, what will happen? The charge on these two spheres will redistribute and it will become how much? Q1 and Q2. So what is going to be same after brought in contact? So please tell me, what is the potential of the sphere 1? Is it going to be k q1 by r1? What is the potential of a sphere 2? K q2 by r2. So after brought in contact, can I say that? So here finally, can I say they are in contact with each other or they are connected by a conducting wire? So they should have what? The same potential of each other. Let's compare it. If I compare it, am I getting kq1 by r1 equal to kq2 by r2? So what is the relation I am getting? Am I getting Q1 by Q2 equal to R1 by R2? Please tell me. Am I getting Q1 by Q2 equal to R1 by R2?
Yes, sir.
K Q1 by R1 equal to K Q2 by R2. Now you see that if R1 and R2 are equal, Q1 and Q2 also become equal, isn't it? If R1 and R2 are equal, then what it will become? Q1 and Q2 also will become equal. So please keep in mind what is going to be same. Potential is going to be what? The same. Charge may be equal, may not be. It depends on the radius of these two spheres that what will be the charge on them. Acha, tell me one more thing. You have written a k q1 by r1. Of this thing you will get it in many other forms like this. I have k q1 by r1 है ना equal to k q2 by r2. Acha, please tell me. Let's multiply r1 and divide r1.
So your screen is not
And
showing.
here, please check it. A screen is not visible. Please check once.
No, sir.
Visible or not? Just check it.
I think you haven't shared it.
Oh, it's showing the screen sharing. Just check it. What is showing on the screen? Nothing.
But your video is.
Okay, let me reshare it once. Yeah, please check it now.
Yes, sir.
So we have a k q1 by r1 equal to k q2 by r2. Left hand side I have multiplied by r1 divided by r1. Right hand side I am multiplying r2 and dividing r2. Do you know what is this written? K q1 by r1 square. Is it the field on the surface is written? Just check it. K q1 by r1 square. Is it the electric field on the surface?
Yes, sir.
So can I write it? This is going to be E1 R1 equal to and K Q2 by R2 square. That is the electric field on that one. So now if they ask you in the question, what is the field ratio? So E1 by E2 is coming how much? R2 by R1 it is coming to us. Okay. E1 by E2, how much is that coming? R1 by R2 we are getting. Another form you can see that. See, same expression I am going to start now. K Q1 by R1, right? Acha, electric field is also written as na sigma by epsilon naught. Please check it. Can we write it? Sigma by epsilon naught also. Chalo, I will do it one more time. K Q1. I can write it from the electric field relation also, but just to make you understand, let me do it one more time. Let's write it R1 multiply R1. Okay? And here multiply R2 divide R2. And what is the K for us? Can I write it? K is equal to 1 by 4 pi epsilon naught. and here also 1 by 4 pi epsilon naught. Please tell me, why did I wrote it like this? Q1, check it, epsilon naught, just cancel it out. Please tell me, what is Q1 by 4 pi R1 square? What is that actually written? Q1 is the charge on the sphere 1 and 4 pi R square is the surface area of the sphere 1. So isn't it? It's written sigma 1 surface charge density, sigma 1 R1. Is it coming to sigma 2 R2? So that means sigma 1 by sigma 2, how much it will come again? R2 by R1. Please tell clear this one. So what you are seeing here, please check it. Whenever the two charged conducting spheres are brought in contact with each other, only one thing is going to be equal for both the spheres. And that is what, this is the most important thing we need to keep in mind. The concept behind this is their potential is going to be equal. What is going to be equal is their potential is going to be equal. Rest other thing like the charge ratio or the field ratio or surface charge density ratio, this may be equal or may not be. That is not necessarily required. Okay, Q1 by Q2, it will become R1 by R2, E1 by E2, R2 by R1, sigma 1 by sigma 2, R2 by R1. Understood? So that's why what happened, the charge density is what going to be inversely proportional to the radius of curvature. Clear? So that's why sometime they will give you a theoretical question like this. They will give you, this is the right. Can you identify in these two cases where the field is going to be strong, where the charge will be accumulated more? Please tell me. Both are equipotential surface. Can you tell me, out of, you look at the surface, okay? This is an equipotential surface, okay? This is what? An equipotential surface, okay? Please tell me, and can you answer me, which place the radius of curvature will be more, R1 or R2? Which place the radius of curvature is more, R1 or R2? R2. Why so? Because the more the flat the surface is, the bigger the radius of curvature will come. Understood? More the sharp a surface is, the smaller will be the radius of curvature. Understood? And you see, charge density is inversely proportional to radius. So can I say in this question here, more amount of charge will be accumulated? Way, can I say that? Because here the radius is smaller and you see the charge density is inversely proportional to radius, isn't it? So here the distribution of charge will be much more denser compared to what? The second part. Please tell me, understood? Can I say that if this point I'm saying the charge density is sigma 1 and this point if I'm saying charge density is sigma 2, can I say that sigma 1 will be greater than sigma 2? So that's why what happened, whenever a pointed surface is there, whenever a surface is more pointed, pointed means what? Sharp surface is there. So what will happen on the sharp surfaces, the charge density is going to be what? More compared to what? the smooth surface, because charge density is what? Inversely proportional to the radius. The condition is what? It should be equipotential surface. So let's say a conductor is there and the conductor has different radius of curvature at a different point. Then what will happen? The surface where the radius of curvature is small means where more pointed surface is there. At that point, what will happen? More charge will be accumulated. Understood? Please tell me, clear up to this? Please tell me, clear what we discussed till now,
Yes, sir.
right? So at the surface of a conductor, the field is how much? Sigma by epsilon naught. Just outside the surface of a conductor, the field is how much? Sigma by epsilon naught. Clear? And the sharp the surface is there, the bigger accumulation of charge will take place. Okay? Clear?
Sir, I have a doubt on one topic. Like
Yeah, tell me.
so the distance between two equipotential surface should be same. Like if a point charge is taken, so the equipotential surface will be the spherical surface, right? I mean the sphere.
Mm-hmm.
So the distance
Mm-hmm.
between two equipotential surface should be same or different.
No, it is not necessarily to be same, isn't it? If it is a sphere, point charge is there, and you are going to find the equipotential surface. Distance between equipotential surface may not be same. Means we can make two sphere of different radius, isn't it? But the gap between the two surface need not to be same. Equipotential surface has what condition? The potential at every point on the equipotential surface should be equal. It never says about what? The gap between two equipotential surface. Understand? So equipotential surface here may have a different gap between them. Okay, so it's not necessary that the two equipotential surface will always have what? Same gap or equal gap between them.
Okay, sir.
Right? So it is not necessary. Okay, so let's meet it tomorrow. Okay, morning time. Tomorrow we have class at the morning time, right? So let's meet it tomorrow and let's discuss the next part of this chapter then. Okay, is that clear?
Yes, sir.
Right. Okay, then take care, everyone, and let's meet it tomorrow.
Yes, sir.